Okay, so the first problem we're going to be looking at here is 17.3. 17.3 is going to reference the illustration that we see on the right-hand side here, and this is found on page 1213 in your book. So for this problem, what we want to do is it says we have two uniform discs, one on either end, okay? And it says that they're attached, with a shaft here. Disc A, which is the front one, has a weight of 10 pounds and a radius of 6 inches. Disc B is twice as thick as disc A. Knowing that the couple, capital M here, and a couple is really like torque, it's a moment, okay? The couple M, with a magnitude of 22 pounds or pound feet is applied to disc A when the system is at rest. So it's starting out at rest, and then this moment is going to be applied to it, or torque. Determine what the radius NR needs to be. Now, if you look, R is the same in both cases. So N is just a multiplier, and that multiplier we're going to have to solve for to get that radius of disc B. When the angular velocity of the system is 480 RPM after 5 revolutions. Okay, so that's the problem that we're going to be looking at. So let's first kind of start off by getting our givens down, getting our finds down, and then how we're going to approach this. Okay, so starting here, this is problem 17.3. Okay, so they are giving us the weight of A is 10 pounds, okay? The radius A, now they're only using R, but I'm going to call it radius A because it has to do with body A, that disc A that's in the front. That is 6 inches, but it's also equal to 0.5 feet. We know that as we work these problems, when we're in English, we need things to be in feet per minute, that kind of thing, okay? Now, we also know that radius B is going to be equal to that factor of N times radius A, okay? Now, what they did, and I deviated a bit, so you can use your best judgment on how you want to handle this, but you're going to notice that they used, for the thickness of these discs, they used the variable lowercase b. We have uppercase B for the other disc. So what I chose to do, because I see this as a thickness, all right, I'm calling this lowercase t A and lowercase t B for the thickness of those discs rather than using B. If you use B, totally fine, all right? I just was a little like, why would they use B for that? I guess we wonder that a lot about the variables that they choose. So I know that the thickness of B, so I'm using lowercase t for the thickness. Again, not trying to confuse things, but only clarify. I know that's going to be 2 times the thickness of A. And we don't know what that is, all right? And we're going to find that it's not really a big deal. It's just a factor that we need to be aware of. We're also given that that moment on disc A is going to be 22 pound-feet, okay? Now, what we want to find, I'm going to put that in the upper right-hand corner then. We're going to find the radius of B, okay? When our angular velocity, I'm going to call it 2 because it's going to be once it speeds up, okay, is 480 RPM and has rotated 5 revolutions. So that's going to be theta 2, if you would, okay? So these are the conditions for which we are going to determine that radius, okay? Now, approach. See, this is where you've got to kind of start thinking, all right, now what am I going to use here that makes sense, okay? I'm trying to find, if you would, an angular velocity. So it makes sense to use the work energy theorem. As we know, we probably could use conservation of energy as well, but I don't know, I think it's a little easier to work with, or it's, I don't know, it makes more sense to me to do the work energy theorem. So my approach, and I think it's important to think about how we're doing this. Sometimes when they jump into especially sample problems, they just start like calculating stuff and you're like, why am I starting there? That's why I'm trying to give you this first. So this is going to be work energy. Okay, which means that this is going to be the T1, which is the kinetic energy initial, if you would, plus the work that we put into the system, initial to final, it's going to be equal to the initial and the final, which we're calling T2, kinetic energy. Now, as stated in the problem, we are starting from rest. So that means our initial kinetic energy is going to be 0. So this really reduces down to the work generated is going to be equal to the final kinetic energy. Okay. Now, it's worth expanding on those based on the problem that we have and the variables that we're going to be using. So T2, our kinetic energy final, is based on a rotating body, right? A rotating body. So we can say that the kinetic energy then is going to be 1/2 times the moment of inertia total of disk A and disk B we're going to find. Okay, so it's the total moment of inertia times the angular velocity of the system squared. Okay, and we're going to be using not the 480 directly, but we're going to have to convert this to radians per second to go in there, but that's going to be that value. And then our work is going to be our U 1 to 2. This is a rotating system. So again, it's going to be using the moment around A, or that torque that's going to be used at A, times the angular velocity or the angular displacement final minus the angular displacement initial. The initial angular displacement is going to be 0. So our theta 2 is going to be what we use down in there. But again, not in revolutions. We're going to have to convert it to radians. We'll see that in a little bit. So this is where we're heading. So we got to look, okay, what are the things that we, need and have to calculate? So we need a total moment of inertia, okay? The total moment of inertia is going to be equal to the moment of inertia of body A or disk A plus the moment of inertia of disk B, okay? Now, because these are solid disks or cylinders that are given to us, as you recall from our equation sheet, we wrote down some generic shape moments of inertia, okay? And this would be a disk or a cylinder is going to be 1/2 mass times the radius squared, okay? So I'm just going to put that over here. Moment of inertia of a disk is equal to 1/2 mass times radius squared. So we're going to need to do that for A and for B, okay? Now, the other thing that we need to consider here is the fact that they told us that the thickness of B is twice that of A. And we also need to find a radius here. So when we start looking at how to relate these two bodies, the thing that we can relate them through is volume, okay? So, for instance, we know that the volume of a cylinder or a disk, solid disk, is going to be equal to capital V, which is pi r squared times thickness, okay, or height. You see it as height, but in our case, that height is the thickness dimension of our disk, okay? So if we look at our disk, okay, center of it, this is going to be our radius, and then this dimension right here is going to be that thickness. I can see that. There we go. Okay. Now, we also know that we are going to need the mass of each one of our disks, okay? Now, the mass is going to be a function of how much matter is there, and it's going to be driven by the volume of each one of these, disks. So what we can do is we can set up a ratio where we say the mass of B going to be, and I'm going to kind of put a little space here. It's going to be equal to the mass of A over here. Now I'm not done on either side. And I want to take, and I want to put underneath here the equation for the volume of B. So using this equation for the volume of B, I'm going to say pi times, now my radius for B is n times the radius at A. Okay, they didn't use RA, but I want to use RA to be clear that that's where it goes back to. So this is gonna be the radius of B, if you would, and we know that the radius of B is equal to n times radius of A. So n times radius of A, and we're gonna square that value, okay? And then we're gonna multiply it by the thickness. Well, we know that the thickness at B is equal to 2 times the thickness at A. So this is gonna be 2TA. See, I already violated my side over here. That's why we use pencil. Equal to. So again, underneath here is the volume of B. Okay, just kind of showing you that. That's the volume of B. Now we're going to set up that same ratio over on the right-hand side, but with the volume of A. So this is going to be pi. This is going to be RA squared times the thickness of A. Okay. And then this is the volume of A, right? Now, as we look here for the moments of inertia of each, I want to get my mass in terms of the items that we have here. So we already can calculate the mass of A because we know that it's 10 pounds. So we have to divide by 32.2, right, Christian, to get the mass. That's always one that you forget. That's the only reason. I'm not trying to make fun of you. But this is English units, so we can find the mass of A. But to get the mass of B, we're going to use what we have here. So now what I'm going to do is I am going to say mass of B. I'm going to solve for the mass of B here. And I'm going to take all of this, okay, and we're going to multiply it up. So I'm going to say the mass of B is going to be equal to the mass of A. Okay. And I'm actually going to get rid of my pi's first because they cancel on either side of the equal sign. So we don't need to worry about that. Okay. But now what I'm going to do is I'm going to take my radiuses and I'm going to put that in the first parentheses here. So that means I'm going to take my N RA and it's squared. I'm going to square the entire quantity in just a minute. And then I'm going to have it over RA here. And then this whole quantity is going to be squared. Okay. Now, as we can see here, because we have RA's top and bottom, they will cancel out. Okay. And we'll be left with N squared, if you would there. Then we're going to take the thicknesses. Okay. I'm going to multiply the 2TA on top divided by the thickness A on the bottom. And we get that same thing happening again. The thicknesses at A cancel out. So I can say that my mass at B is going to be equal to mass at A times 2 times N squared. Okay, if you want to write it that way. There's different ways you can write it, but essentially that's what it is. So now I know the mass of A. So I can say, all right, I'm going to take my 10 pounds, I'm going to divide it by 32.2, divide by gravity. I'm going to multiply that by 2, and then I'm going to have N squared out there. So doing that, I can say that my mass at B is going to be equal to 0.62112 N squared. Okay. Now, this is not a final answer, but, and there is a variable in here. This is not newtons. This is just the N variable or the multiplier when we want to try to find that radius later on. Okay. Now, this allows us to plug that value in when we need to for the moment of inertia of disk B. Okay. So, let's see how long. Okay. So our next thing to do is we want to calculate each one of these moments of inertia of A and B. All right, so that's going to be our next step. So moment of inertia, we'll do A first. We'll do moment of inertia of A is equal to 1/2 mass of A times the radius of A squared. Okay. This is going to be 1/2 times 10 divided by 32.2 times, now don't forget, this is going to be 0.5 feet. I'm just going to put feet in here so that you don't put the 6 inches in there. Otherwise, things won't come out. Everything has to be in feet for our lengths, and that's going to be a quantity squared. So you should get your I at A 0.0388 pound second squared times feet. Okay. So that's an actual value. You have a number calculated for a moment of inertia of A. Now, moment of inertia of B, same base equation, okay? Mass of B times the radius of B squared. Okay, now this one is going to be equal to 1/2 times. Now, on the previous page, this is the mass that we're going to put in there, and it's multiplied. Don't forget to multiply it by n squared. So this is going to be 0.62112 n squared. Okay, that's my mass. Times n times 0.5. This is the radius of A. So this is the radius of B, remember, is equal to n times the radius of A. Radius of A is 0.5 feet, and we're going to square that value. Okay. Now, what's going to happen here is you're going to get a number for IB, and you're going to calculate it, all right? I'm not going to give you this number. You're going to calculate your value, and it's going to have a variable that is n to the 4th power, because you're going to have n squared here times n squared there. It's going to be n to the 4th, okay? And then it's going to have units of the pound second squared, okay? So you're going to be doing this. So again, I'm doing setup here. I don't want to give it all to you. I want to give you that opportunity to get it in order, okay? Now, once you have your moments of inertia, let's go back to our work energy theorem so you can see how we can develop this. So we're going to have our work 1 to 2 is going to be equal to T2. All right. We know that our work is the moment at A, capital M, I don't want the, times theta 2 is equal to 1/2 I total, okay, W2 squared. Now, I'm going to tell you, W2 needs to be in units of radians per second. You'll have to convert the 480 RPMs to radians per second. So you have to convert your W2, okay? Additionally, your theta 2 needs to be in radians as well. So these are the units. You are given theta 2 in revolutions. You have to convert that to radians, okay? Once you have those done, you're going to plug in the values that you know, and you are going to solve for the total moment of inertia. You will be able to, I'm going to tell you this, I'm going to give you this as just a suggestion and a tip to make it go a little bit easier. Do not plug in your A plus B right away for your total moment of inertia. Just solve for what the total moment of inertia is as far as a number, okay? And once you get that total moment of inertia, you're now going to say, all right, the total moment of inertia is equal to IA plus IB from before, and you'll have one unknown variable of n. So then you'll solve for n, okay? Does that make sense to everybody? If you try to plug the A and the B in here, I'm going to tell you, I tried it. I tried it 3 times and I just kept getting lost in all the decimal places and the numbers and all that kind of stuff. And I just found that this was the easier way to go. So I would just solve for my actual value of my total moment of inertia, then set it equal to this plus this, and then solve for the n at this point. Just a lot easier than the headache of all the stuff. Okay. And it came out then. Okay. Your n should come out to be 1.5996. Okay. And it's just a variable. It's just a, there's no units there. Okay. And then you're going to use that, your RB is going to be equal to N times RA. So then once you get that value, you can plug it in there. And then remember that RA is 6 inches. Okay. I think the final answer is in inches. So use the 6 inches times that N value and you should be in good shape. So that's the setup. I think that gives you hopefully really good direction on, first of all, the approach and kind of how to go in the process to go through to get it solved without robbing you of the opportunity to do it yourself. So is that helpful for those who maybe needed some guidance? Okay, good. Josh's
but I saw.
Yeah, this is helpful.
Oh, yeah. Yeah. Yeah, the volume worked well. It worked well. Christian.
For the theta value, should that be in radians?
Yep. Yep, I did state that right here.
Sure.
That's okay. Yep. So right there. So when you have your theta in here, it has to be in radians. And then the angular velocity also has to be in radians per second. So you're given it in RPMs. It's kind of like if you remember from kinematics, whenever we were using it in any equations, right, we had to do that conversion. So yeah, make sure you do. Any other questions? Okay. All right, then I will stop the recording here.